Okay. Screen is visible to you?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
So now we'll start the second part of the bridge foundations, that is the pile foundation. We have seen open foundation. Now we'll go to the pile foundation. Now, depending on the manner in which the piles transmit the load, they can be divided into three categories. What are those categories? One is end bearing pile, where this load from the top or from superstructure through the pile, it rests at a hard stratum and it is resisted by end bearing resistance here. So these type of piles always have to rest on a firm soil or rock, mostly in the rock and sometimes firm soil also, when you get the required end bearing resistance. And they primarily transfer the load by bearing resistance developed at this location at the toe of the pipe, and the friction along the shaft of the pile is not taken into account or is not mobilized. So this is first type of piles. Second type of piles are known as friction piles. In these piles, this load Q is resisted by the friction between this pile shaft and the soil surrounding it, and the summation of this friction along the total surface of the pile resists the load. So these piles, they transfer the load primarily by the skin friction developed along their surface. Along their surface, whatever skin friction is developed, that will resist the load. And the third type of pile is a combination of both end bearing or bearing cum friction piles. So partly they resist the load by end bearing resistance at the tip or toe of the pile, and partly by the friction along the shaft of the pile. So these are the type of piles depending on the manner of load transmission. Now the categorization of pile based on the method followed for construction. Regarding casting of the pile, there can be two things. One is precast. You cast the pile somewhere else and then bring it to the site and put it in position. So precast pile. And another is cast in situ pile. Cast in situ means at the site itself, you pour the concrete and you put the reinforcement if required and cast them at the site. Similarly, the way you put the piles in position, there can be two methods. Driven piles, where you drive the pile or part of it into the ground. Driving means pushing it. And bored piles, where you do a boring on the ground and then pour the concrete and put the reinforcement in place. So this is based on casting, this is based on putting in position. So theoretically, how many combinations are possible? If we mix and match these two, this based on casting and this two, how many?
Four.
Four, right? So there can be precast driven, there can be precast board, then there can be cast in situ driven, and there can be cast in situ boards. Theoretically, four combinations are possible. Now, actually, is it done? Let us see. First is precast driven. Very simple. Your pile is casted somewhere, it is brought to the site, and then it is driven into the ground. Let us see a video of this type of piles. You are able to see the video?
Yes, sir.
Yes, sir.
There is no sound in this, so don't worry. So this is your pile which is casted somewhere else. You bring it, you put a bulkhead on the top, and then through some impact load, you apply it continuously and you push the pile to the required level. like this, and then you put pile cap over that and your load transmission and all. Very common. But what are the issues in this? Number one, they are normally used for lightly loaded structure. For heavy structure, they are not very suitable. Second thing is, here the handling stresses are very high. So a large amount of your pile capacity goes in handling itself. Let us say you costed in depot 6 meter long pile, how you will lift with 1 sling or 2 sling or 3 sling, whatever. Then there will be handling forces in transportation. Then when you drive the pile also, there is heavy blow here. So maybe this area you need some strengthening, otherwise your concrete may get damaged here and all. That is one problem in this type of piles. What is another problem? Can somebody tell what can be another, what is another issue with these piles?
Sir, disturbance in the soil.
Yeah, it causes disturbance in the soil, and therefore some part of friction also is destroyed in that part. There is one more big problem in that, in these type of piles.
Sir, adjacent piles can also be disturbed.
Yes, adjacent pile also can be disturbed. Very correct. One more thing, something I'm looking which is very, which makes
So
it a
pile
handicap.
itself can be disturbed.
Pile itself
Can be damaged.
yes, it can be damaged. Yes, agreed. That's why I said handling stresses are very high. The another biggest problem is there is no flexibility in the pile length. Let us say you have to do piling in this area. Every inch you don't do soil investigation. Maybe you might have done soil investigation here and you found that your end bearing strata is coming at 10 meter. And when you are using this soil investigation, maybe 2 meter away, here you may need 11 meter. But your pile is constant in length. Whatever you have casted, at least you cannot increase. Decreasing also is very difficult. Maybe theoretically you can decrease by breaking or cutting, but that is also difficult. Increasing is certainly ruled out. So that flexibility of pile length as per your site requirement is not there in this type of piles. Correct?
Yes, sir.
Therefore they are used. हम घरों में बहुत बार भी may not call it pile, जो खूंटा गाड़ते हैं उसके ऊपर कुछ load है, many times we use that is nothing but a precast driven pile. So this is first type of pile, that's why they are used for lightly loaded structure. So this combination we have seen, precast driven. Now cast in situ driven, interestingly, how cast in situ driven pile is casted, let us see a video. You are able to see the video and get the sound both?
साउंड नहीं आ रही है
वीडियो आ रहा है, साउंड भी आ रहा है?
वीडियो आ रहा है सर.
We are just getting the background noise from your end.
साउंड नहीं आ रहा?
No, sir.
Huh?
No, sir.
It's background noise, some driving noise. So, that's what we are not getting. Yes, no, क्या?
सर आपका क्वेश्चन सुनाई नहीं दिया.
Are you able to see the video and get the background sound which is there in the video? जो driving का sound आ रहा है या उसके ठोकने का जो sound आ रहा है?
Sound नहीं आ रहा,
We're
सर
just
मुझे
getting
दिख रहा है.
the audio.
वीडियो विजिबल है सर, कोई ऑडियो नहीं आ रहा है. Okay.
Yeah.
Yes, sir.
Yes. Are you getting sound now?
Yes, sir.
Let us play from beginning, from here.
आवाज नहीं आ रही सर अभी।
First of all, whenever you then this pipe to this oil pipe. Then you pour the concrete from the concrete and extract that. And then you lower the reinforcement. ठीक है?
Yes sir.
Now, what can be the problem in this? What is the anticipated problems in this?
सर क्वालिटी इंश्योर नहीं हो पाएगी।
Which quality? What part of quality?
सर जो कंक्रीट कास्ट किया जा रहा है सर वो अब हम देख नहीं पा रहे हैं कि मतलब अंदर जो चीजें जा रही हैं कि प्री कास्टेड में सारा कंट्रोल पैरामीटर हमारे हाथ में रहता है।
Okay, that is there in every cast in situ method. That is the, of course, one of the limitation of every cast in situ system. But in addition to that, what other problem?
Sir, I think railway bridges dewatering ज़्यादा टाइम के लिए हमें वो मेंटेन करना पड़ेगा. That would be difficult.
कंस्ट्रक्शन स्लो हो गया.
Construction.
Enforcement का alignment में भी.
That is the biggest problem in this. Number one, if your pile is very, very deep, maybe more than 15-20 meters, it will be very difficult to put the full reinforcement. So when your pile capacity required is more, these piles may not give you that capacity. For you to put length of reinforcement in full length will be very difficult. Second thing is, उससे धक्का मुक्की करके जब reinforcement को अंदर घुसाएंगे, there is chances of reinforcement getting disturbed. आपने उसकी जो टाइज लगाई थी, जो भी किया था, how do you ensure exact cover? How do you ensure the exact alignment of reinforcement? That is likely to be disturbed. So again, this is used for some lighter structure or not very deep piles, but they are not commonly used for railway bridges. Okay. Now,
Excuse me sir.
Yes.
सर इसे हम ड्रिवन क्यों कह रहे हैं? इसमें ड्राइव क्या किया हमने सर ग्राउंड में?
Casing drive किया ना पहले. You have driven the casing and then casted your pile. You have driven the tube and then casted your pile.
Okay sir. Okay.
So ये दो हो गया, प्री कास्ट ड्रिवन हो गया, कास्ट इन सीटू ड्रिवन हो गया. तो ड्रिवन तो दोनों हो गया. अब आते हैं बोर्ड पाइल में. बोर्ड पाइल में कास्ट इन सीटू बोर्ड. ठीक है. कास्ट इन सीटू बोर्ड मीन्स आप पहले ग्राउंड में एक बोरिंग करेंगे, उसके अंदर फिर पाइल कास्ट करेंगे एट द साइट. these are the most commonly used type in Indian Railway. Most of the things which we'll see later on are related. They are most commonly used, not only railway, other places also. This type of piles are most commonly used. अब चौथा combination cast in situ driven तो हो गया, प्रीकास्ट, हाँ प्रीकास्ट बोर्ड हो सकता है क्या? How it will be? प्रीकास्ट बोर्ड मतलब पहले आप पाइल को कहीं कास्ट कर लेंगे, यहाँ मान लीजिए आपने कास्ट कर लिया, देन दिस इज योर ग्राउंड, फिर आप एक इसमें बोरिंग करेंगे, फिर इसके अंदर इस पाइल को डालेंगे और फिर बाकी मिट्टी भर देंगे. दिस इज व्हाट इज मीन्ड बाय प्रीकास्ट बोर्ड. ऐसा हो सकता है क्या?
सर हो तो सकता है बट प्रैक्टिकली इनफिजिबल है और प्रॉपर स्ट्रेंथ डेवलप करने के लिए.
यस यू आर राइट, हो तो सकता ही है, क्यों नहीं हो सकता, बट इट विल बी अ फुलिश थिंग टू डू. इसमें आपका न तो स्किन फ्रिक्शन मोबिलाइज होगा, हैंडलिंग स्ट्रेसेस, बट इंसिडेंटली लेट मी टेल यू, वंस इन माय लाइफ टाइम व्हेन आई वाज इन ट्रेनिंग आई हैव सीन such kind of work being done incidentally in Central Railway only. यहाँ दौंड के पास में लोग खड्डे खोद के उसमें प्रीकास्ट, and I was shocked. So normally this is not done. उसके बजाय तो उसको ड्राइव कर दो आप. At least air friction is almost lost, and then all other disadvantages of driving and handling and all those things. So most common is this, and most of our discussion will be on this cast in situ board piles. They are flexible, you can cast them to the required depth, your reinforcement gets placed in position tightly, it does not get disturbed, and you can do so many other things. As we go along we'll see. So now seeing them precast driven pile, again we have already seen advantage also. Of course there are some advantages. Pile can be inspected before driving, you can see the pile ki pile theek taak hai. It is not liable to squeezing or necking. You know, in cast in situ, that is the biggest problem. You first make a bore. Either it may happen like this, bore collapses like this. You may be putting concrete in this, only some concrete may go here, or maybe your bore there is a necking here. So your pile will not be of the required cross section. That is avoided in this part. And construction is not affected by groundwater. You can keep on driving in the groundwater also. You don't have to do most of the time any special dewatering arrangements. Disadvantages, as I told you, pile may break, it may suffer unseen damages during driving, it is uneconomical due to high handling and driving stresses. If you see design of this precast pile, it's most of the reinforcement is from handling and driving stresses point of view. So only for an incident which will happen initially once and throughout its life which will not be used, but you have to design and provide reinforcement accordingly. So uneconomical. Noise and vibration issues, they create lot of noise. So if you are working in some nearby where people are living, they will come with a dandas and beat you up. It will cause lots of vibrations. And as I told you, skin friction is almost destroyed in this process, especially in clay soil. Cast in situ board pile, which, as I told you, are most commonly used. Advantage is you can adjust the length easily. Enlarged base is possible. You know, there is a type of pile where this is your pile and your base is enlarged by design. What are these piles called?
Under-ream piles.
Under-ream piles.
So it is possible to construct under-reamed piles only by this technology. There is no handling and driving stresses. You are straight away putting it here. Vibration and noise are lesser, I will say, not nil. But disadvantage is, as somebody has said, defective concrete in shaft may go unnoticed. If anything wrong has happened with concreting, segregation, bleeding, or anything else, you are putting concrete in a black hole. You are not able to see. Of course, some methods have been devised to see them, but they are still not, I must say, 100% foolproof. Concrete cannot be inspected after installation, what happened to concrete, and it requires special adaptation for use in river and marine structures. That is what underwater concreting we say, and we'll see it, how it is done. So wherever water table is high and you have to go below that level, you require special arrangements for dewatering and then, you know, putting concrete in those locations. So now we will see what are the various methods. As I said, we do cast in situ board. So how the various methods of doing boring and then casting the piles, the most commonly used methods. First is chisel and baler method. Second is called DMC, direct mud circulation method. Third is called RMC, reverse mud circulation method. Then there is CFA method, continuous flight auger method. There is cluster drilling method. We'll see them briefly, all of them one by one. These are the most commonly used method wherever you see this sort of. And as I told you, most of your location, 99.5% or maybe almost 100%, you will have bored cast in situ piles wherever piling is being done. So first see chisel and baler. This is most common, most of your sites, especially other than cities and most of the bridges, sometimes in cities also. This is bread and butter of piling system. Whatever piles we have done mostly through this method. So what is done in this method? In this method, this is your ground. First you make liners of steel plate. You bend the steel plate, 6 mm, 8 mm normally is used. You design depending on up to what depth you have to go and what is dia of pile. You bend it to a circular shape, and then this is called liners. So you drive the liner to the required depth or wherever refusal comes. Sometimes refusal will come for liner. It means hard strata has come. After that, through this liner, you will do boring. And for boring, you use chisel and baler. This is how your chisel looks like. It is a heavy pointed tough iron thing, very heavy, weighs about a ton, not a ton, around I think 300-400 kg. So there is a tripod. From this tripod you hang this chisel, and this is operated either by using manual pulley system or winch. So you will drop this chisel. When you drop this chisel many times, it will pulverize this soil. Then after that, after sufficient amount of ground is pulverized, you use this, what is known as baler. It is a cylindrical thing with a flap at the bottom. So then from that pulley, same pulley, you remove the chisel, you hang it on this tripod and connect it with baler. And then you drop the baler in this same borehole. When baler comes down, because of upward air pressure, its flap opens at the bottom, and whatever is your pulverized material here, it gets collected in the baler, even below water level also with that sort of slurry. Then baler is taken out and you remove that material and again put the baler. So it is a sort of what you call continuous operation of chisel and baler. First you pulverize with chisel and then with baler. Even very hard rock also takes time. Progress is rough, but this is the method followed. So up to whatever your required depth, you go up to that required depth. You will do boring first. Then whatever flushing of bore, cleaning and all, there are operation. After that, you lower your reinforcement cage here. Reinforcement cage is made outside. It is brought. There are spacer blocks and all those arrangements. You lower your reinforcement up to whatever depth you designed the reinforcement. Then this is known as underwater concreting, trimmy concreting. We will see how trimmy concreting is done. So you put your trimmy pipe up to bottom of the pile and put concrete from here. As you keep on pouring concrete at the bottom, you keep on lifting this pipe, and then you do concreting up to here. In fact, you do after this also. You don't stop here. If this is your ground level, I will tell you also, normally you take something for development length, because finally you have to cast the pile cap. So for that much you have to take reinforcement outside. And then in addition to that, see what happens is the top portion of this concreting will always carry some latence, the mud and all from the bottom. I will tell you in trimmy concrete, that is not good concrete, so you chip it off. So normally whatever is your design cutoff level, above that some level you do concreting up to here, and this is later on chiseled off and thrown away, because that's not a good quality concrete. So this is how you do your concreting, and your pile is ready. And then once a group of pile is ready, you put reinforcement for pile cap and cast the pile cap. This is how this, you can see here chisel is working, and then chisel can be hanged from this, and same thus it is unhooked. There is a D-shackle here. There is a shackle like this. There are bolt and this is the wire. So you remove this bolt, remove it and put the hook of chisel and baler. And here you can see the winch. Nowadays manually nobody likes to work. So there is a winch, and with their diesel driven winches most of the time your pile driving is done. Okay? chisel and baler method works?
Yes, sir.
Yes, sir.
मोस्ट कॉमन आप साइट्स पे देखेंगे या जो यूज करेंगे मोस्ट कॉमनली आपको यही मिलेगा. Then there is a direct mud circulation. It is actually an addition to chisel and baler. It is not a different method. It is a supplementation to chisel and baler method. So why it is necessary? Because of 2-3 reasons. Number one, when it becomes difficult to bore using chisel, your time required is very high, your ground strata is very firm, then you use what is known as bentonite slurry. This does two functions. Bentonite is a type of thixotropic clay. Its particle size is very, very less, that is one. So it acts as it is also known as drilling fluid or cutting fluid. In bore, when your chisel is coming and hitting here, this bentonite slurry, small particles, they act as a lubricant and helps in cutting the surface, that is one. Second thing, bentonite, because of its nature, if you take bentonite slurry and let us say this is a pit made and you put bentonite slurry in this, you keep it still for 5-10 minutes, you will find it makes a thick surface here. It of course makes a thick surface here which develops lot of surface tension, and you can put some small weight also. आधा किलो का weight भी रख देंगे तो हो सकता है नहीं गिरे. It develops a sort of thin film around that. But again एक डंडा लेके आप इसको जोर से हिला दीजिए, again it becomes like a liquid. So it has got this property. तो इसके कारण when you use bentonite here, this bentonite forms a sort of film all around your bore. If you see in plan, this bentonite film will be formed all around the bore, and it helps like a semi-liner. It is not exactly a metal liner, but still it helps like, and it helps in stabilizing the borehole walls. छोटा छोटा ये जो यहाँ से गिरता है borehole, उसको रोकता है. So that is the only difference in DMC. You call it DMC method. Why DMC? I will tell you. So then you use bentonite slurry to help in boring as well as stabilizing the borehole. These are the two functions which bentonite slurry does. So there is a pit made there. From that pit,
Sir,
you yes.
सर जैसे आपने बताया एक लाइनिंग क्रिएट कर लेता है. अब सर सपोज जब हमारी कंस्ट्रक्शन पूरी हो गई, वहां पे वाटर आ जाता है, इनग्रेस ऑफ वाटर है सर हमारा सॉइल में, तो सर उस केस में तो बेंटोनाइट बिकॉज बहुत एक्सपेंसिव होती है सॉइल, तो एक्सपैंड करेगी, दैट वोंट कॉज एनी प्रॉब्लम बिकॉज सर फ्रिक्शन हमारा इंक्रीज हो जाएगा. बट अगर वहीं ड्राई उसके बाद जो ड्राई स्पेल आएगा सर उस केस में तो फिर फ्रिक्शन
होती है. द थिकनेस ऑफ दैट फिल्म इज इन माइक्रोन्स, लेस देन मिलीमीटर, तो उसमें कोई स्वेलिंग नहीं होगी. एंड सेकेंडली व्हाट हैपेंस इज व्हेन यू पोर द कंक्रीट, आप अभी जैसे आपने ये बोर बनाया, इस बोर की जब ये बोर खाली है तो यहाँ एक थिन फिल्म है, वेरी वेरी थिन फिल्म, एंड व्हेन यू पोर द कंक्रीट, इन एनी केस कंक्रीट विल डिस्ट्रॉय दिस फिल्म एंड इट विल बी फिल्ड विद कंक्रीट. इट विल गेट फिल्ड विद कंक्रीट.
ओके सर, थैंक यू सर.
फ्लश कर देगी. व्हेन कंक्रीट गोज डाउन द फिल्म मोस्ट ऑफ इट गेट्स फ्लश्ड. ओके, तो ये बेंटोनाइट आप बोर होल में आपका जो है डालते हैं और फिर वापस इसको यहीं से रीसर्कुलेट होता है, बोर होल में जाता है फिर वापस आता है. एंड इन दिस प्रोसेस सम सॉइल आल्सो गेट्स मिक्स्ड एंड दैट्स व्हाई योर बेंटोनाइट गेट्स कंटेमिनेटेड. इसकी डेंसिटी चेंज होती रहती है, तो यहाँ आप इसमें पिट में इसकी डेंसिटी चेक करते रहते हैं. व्हेन डेंसिटी बिकम्स क्रॉसेज ए थ्रेशोल्ड लिमिट, फिर आप उसको बेंटोनाइट से रिचार्ज करते हैं. यू पुट फ्रेश बेंटोनाइट एंड दिस इज हाउ it keeps on going. So this method is known as direct mud circulation. इसमें आपके यहाँ जो चीजल या बेलर जो भी है उसमें बाहर से बेंटोनाइट आ रहा है और इसके अंदर से निकलता है. This is the path. So sorry, उल्टा, direct mud circulation. So इसके अंदर से आता है. This is your slurry tank. इस आपका चीजल या बेलर जो उसके अंदर एक ट्यूब होती है उससे आता है ये, और एनुलर स्पेस जो है बाहर से उससे ये निकलता जाता है, which again you take to your tank. And in settling tank, because your soil is heavy, तो कुछ तो सस्पेंशन में बाकी कुछ चीज यहाँ से हो जाती है सॉइल, यहाँ बेंटोनाइट रहता है. तो यहाँ इसकी डेंसिटी you keep on checking continuously, and when it becomes more than a limit, we will see those limits also. You recharge the bentonite and after some time you remove this heavier particle or settled things there. So that's why it is known as direct mud circulation. Mud comes from your chiseling tool, and then it is circulated from outside. This is the only improvement. So it is chisel and beller or any other method, whatever method you are using, through that method you circulate the bentonite. That is the only difference in other methods and this method, and this is called direct method. So most of the places you will find it is chisel and beller with DMC. Most of the places you will find your method which is used is chisel and beller with DMC. So bentonite is a clay of formed morillonite group. When the dispersion is left to stand undisturbed, it forms thin jelly-like mass or membrane which helps in stabilization of bore. When jelly is agitated, it becomes fluid again. And the specific gravity of freshly prepared bentonite is between 1.03 to 1.1. Fresh, when you make bentonite slurry, this is the density, and the density of bentonite suspension after contamination with the material in the bore may rise up to 1.25 grams per milliliter, which should be brought back to 1.12 gram per milliliter by flushing before concreting. So you keep on checking it, and whenever it becomes more than your this limit 1.25, you will recharge it. And there are two stages of use of bentonite suspension. First is flushing during boring. So during boring, continuously your hole is bore hole is getting flushed with this. And second flushing is for cleaning the bore hole after completion of boring. After you complete full bore hole and you bring out your chiseling tool and all, then also you do bentonite flushing by putting a tube here. You flush it and take it out from there by. From force, from top you put, so from sides it will come back again, you will push out. You will clean the bore hole with this. So this is how DMC is used. Another is RMC. RMC rigs are sophisticated rigs and they are costly, they are not readily available. Some places you may have RMC also in place of DMC. Their advantage is these rigs have larger capacity, mud pumps they are used, and air compressors are used to allow for increased pressure that are needed to ensure removal of cutting. Sometimes when your material is heavy or your bore dia is bigger, mostly in those cases, there everything by normal pressure and gravity you are pumping the thing out. Here, when you are not able to lift your cuttings and other things, in that case you use RMC method. In this method it is ulta. If you remember, in previous method, this your fluid was coming like this and going out like this, whereas in this method it comes from annular surface and then it goes through this. That's why you need mud pumps and air compressor and all, otherwise it will not be possible to use this. So here the drilling fluid flows down outside the drill rods and passes upwards through the bit, and cuttings, the ground cutting or strata cutting, are carried into the drill rods and then they are discharged back into mud pit. Then mud pit and other things are same, but its flow direction is annular space through drilling tool. That is the difference. And the hydrostatic pressure of fluid column plus velocity head of downward moving fluid outside the drill pipe supports the bore hole well. Here support action is more because what happens is, one of course bentonite may be. Second thing is you have to force it with pressure. So some pressure is exerted laterally also. You have to use air compressor and mud pumps and all. So that also helps you in stabilizing or supporting the bore hole better. And often to aid upwards movement of the water through drill string, air is injected, lifting the contents to the surface. As I told you, when your bore dia is more, cuttings are more, compressed air is also injected many times. With that it gets lifted. And as I told you, there it is normally required or used for bigger dia piles. So normally in railway our diameter of pile is 1 to 1.5 meter. 1 and 1.2 meter are most common. Some cases we go 1.5. These are two standard, 1 meter, 1.2 and 1.5. They are most commonly used dia. So RMC is a cost-effective method for drilling bore hole of 24 inch and more dia. So it is basically more suitable for higher dia piles. Normal dia piles, it may not be economical, and it's most successful in unconsolidated formations. When your ground is unconsolidated, cohesive soils, then this method becomes effective. So this is the difference between DMC and RMC. I will show you a video of RMC also. You are able to see the video and get the sound this time?
Yes, sir, वीडियो तो आ रहा है, साउंड भी
Sound क्यों नहीं आ रहा? It's a hell lot of trouble every time this sound error comes. Or let me play it from here. This may work.
The reverse
This time you are getting sound?
circulation drilling system
Yes, sir.
is like any of the other systems profiled, in that it is a very large rig, requiring a big footprint for both the rig itself as well as the machine-dug settling pit. These rigs are primarily associated with drilling large diameter wells in unconsolidated material, ranging from 24 inches to 50 inches in diameter and up to 1,000 feet deep. The cutting actions used in the reverse circulation system include the rotary cut and the rotary crush actions. Shown here is rotary cut. The unique direction of the water-based flushing media is profiled. This fluid is sent down the annular space between the drill string and the borehole, removing cuttings back up the drill string and into the settling pit. This pit must be very large to accommodate a sufficient amount of fluid, which is required to flush the large amount of cuttings generated in drilling a borehole of this diameter. The excavated material needs to be replaced with fluid as drilling continues, further increasing the quantity of fluid required for this drilling process. In addition to the makeup fluid required, a significant amount of fluid is displaced and lost in the original formation, as this system does not typically use bentonite and therefore does not entirely seal the hole during drilling. While increasing the demand for liquid used during borehole construction, this system has the advantage of reducing development time as compared to traditional mud rotary drilling.
So in this system, it is not necessary that you always, people sometimes use bentonite. Even if you don't use bentonite also, you can work. You have to give extra pressure and all, of course, for aiding and drilling. But it is not necessary that you use bentonite in RMC, whereas in DMC you have to use bentonite. Okay, clear?
Yes, sir.
Okay. Now come to next, continuous flight auger. As I think it must have been told to you in geotechnical investigations last time when you were here. Continuous flight auger is a type of auger where there are spirals on the side of auger. There will be a stem. There will be a spiral on side of this. There can be solid stem CFA. There can be hollow stem continuously flight auger. So these type of augers are used for boring in the ground, and then you do concreting and other option. So this is how there are in CFA also. There can be many techniques. Basically CFA name is because you do boring using. This is one of them. Let us say this is your CFA. So using this CFA, first you put the CFA at your required spot, so spotting. Then this rotates CFA. In that process it goes down. The board material comes out from here. So you do drilling. Then this is hollow stem CFA. So through the stem of the CFA, it can be solid stem CFA as well. You may withdraw the CFA and then like your normal cast in situ pile, whatever board cast in situ you can do. But in this case it is hollow stem CFA. So concrete comes down this stem and you fill the concrete and progressively you withdraw your auger, CFA, continuous flight auger, and then you can lower the reinforcement. Another thing, as I told you, you can lift this, keep the bore, put the reinforcement, and then also you can do the concreting using trimming and all. So there can be different variations of this. And this is a video of CFA. Let me play from there. I hope it will work. Yeah, CFA. You're able to get the voice and see the video?
Yes, sir.
Yes, sir. Yes, sir.
Yes, sir.
NSCC possessed a specialized fleet of drilling rigs of high torque and pull-down capability. The drilling and concrete process is electronically monitored and visible in the operator cabin. This includes, among others, pile inclinations, drilling and concrete pressure. CFA drilling is an established methodology of bored piling that is fast, economical and environmentally friendly. It is suited for most structures. A Kelly extension allows for extra depth to reach 26 meters of drilled pile. The use of compressed air through the augers allows penetration into hard grounds, usually not associated with CFA piling. Upon reaching the desired depth, the concreting process is commenced. This is controlled through the same electronically monitored system. The augers are pulled out whilst monitoring the electronic system to ensure quality. Unlike open bored piles, the reinforcement cage is installed after the pile has been concreted. A cage is lowered into the concrete pile with the assistance of a hydraulic vibrating hammer until it reaches the predetermined depth. The data gathered through the drilling and concreting process can then be shared upon request.
Okay.
Yes, sir.
Then another method is cluster drilling method. Actually, in CFA and cluster drilling method, they are like normal bored cast in situ pile. Only the drilling methodology or creating the drill or bore hole only is different. So in cluster drilling, other all things remain same, like your bored cast in situ pile. First you drive your casing, then through casing you will do the drilling. Only thing is this drilling tool is different. This drilling tool is a cluster tool. In fact, all the metros if you see, especially like Pune metro and other things also. Number one, it is very effective. It produces less vibration. यहाँ सिटी में आपने चीजल एंड बेलर चालू कर दिया धमाधम तो people will not allow it. That is one. Second thing, it can drill through hard rocks also very efficiently. So these are, and you can drill bigger dia pile also. जैसे मेट्रो में शायद 2-2 मीटर तक करते हैं कई जगह. So that's the only difference. Otherwise, it is almost same. So you have done the drilling. Then after reaching up to the required borehole depth, you put the casing pipe, and then you pour the concrete by Tremi method or whatever is the method. And sometimes people withdraw the casing, sometimes you allow it to remain there, because withdrawing casing is not so easy. It may require more effort, but there are some places where they withdraw it because now casing is not needed. So that is the simple. The only difference is this drilling methodology, which uses a cluster hammer. So I will, yeah, this is the video of using cluster. Metros, all metro where they do piling, you will find mostly they are doing this. Get the video and hear the sound.
Yes, sir.
Sir.
Yes.
Piling Contractors has developed cluster drilling techniques to allow us to drill very hard rock up to 400 MPa strength, which is around 10 times harder than normal concrete. The technique uses a special drilling tool called a cluster hammer. This tool is typically operated from a hydraulic trawler-mounted piling rig. The cluster hammer is made from several individual downhole hammers combined together in one barrel. The downhole hammers are activated by high-pressure airflow provided from compressors and piped through hoses to the drill stem. The compressed air flows through the hammer bodies, activating button bits at the hammerheads, and then flows back up the small gap between the cluster drill and the sides of the pile bore. The hammers fire at up to 1,200 times per minute, pulverizing the rock into small cuttings. The upward airflow lifts the rock cuttings and carries them back up the pile bore. A change in airflow velocity occurs when the airstream passes over the top of the cluster drill body, and this causes the rock cuttings to drop out of the airflow into an open-topped calyx basket at the head of the cluster barrel. The basket is progressively filled with rock cuttings as the drilling proceeds deeper into the hard strata. Once the bucket is filled, the cluster hammer is lifted from the bore. The rock cuttings are emptied from the calyx basket. Then the cluster hammer is lowered back into the bore to continue drilling. This drilling process can be carried out in dry holes or under a head of water or other support fluid. Piling Contractors. Think safe, work safe, home safe.
Okay, clear?
Yes.
Right.
Yes.
So this was all about process of, boring and sequences and all. Another important thing which I told you is underwater concreting. In most of the locations, especially in coastal area and even in, except maybe some dry area like Rajasthan or somewhere, or some parts of Gujarat, if you go to deserts, you will find your pile end or pile tip or founding depth is below water table. And once you have made bore up to there, you have to do concreting underwater, in the water. So the most commonly used method for concreting underwater is Tremi concreting. This is most common and proven method. So it is a method for underwater concreting. We will see how it is done. So first, let us say you have made borehole up to here. Then these are the Tremi pipes. They come in 1 meter length or so, and there are joints between them. So you can join one pipe with another pipe like that and make of any length, whatever possible. So you will join these Tremi pipes and take them up to just near to the bottom. Then on top, there is a hopper which is connected. The last segment will be hopper. And then previously the system was, there used to be a thread from here, and the end of that there used to be a rubber ball of the dia little bit bigger than Tremi pipe, so that you push it and it keeps it closed. Nowadays a flap system is also coming. There is a sort of flap which can be closed and opened from string from here. Then you will fill up concrete, and most of the time it is pump concreting. By pump you will, or if you are working in dry area, maybe it comes directly RMC with very high slump value. You will see these values and all because it has to flow freely. That is more important requirement. If it settles in the tree, whole thing you are finished. So this concrete. So now because of this obstruction here, this hopper will remain filled up to here. Now this depth at what it is to be kept is standard, the manufacturer tells you. Then after sufficient amount of concrete has come, what you will do is you will either, there are various methods, sometimes you remove this, but removal is difficult, but it is designed in such a way when sufficient force comes, this will push the bolt down at that weight of concrete. And now this much weight of concrete is falling and it gains some velocity also. It comes here, it falls here with a thud. Its density is more, whereas existing was water with some mud and all. So it will, that water and mud will start floating on the top, and this concrete, which is heavy, is dropped at the bottom. And you have to always keep the end of tremie in the concrete. You should not take it out. That's the essential requirement. Otherwise, what will happen is, let us say if there is a gap, then this lattice will get sandwiched between two good layers of concrete, and that is a place of weakness. So your tremie pipe end should always remain in concrete and lattice will be on the top. So you keep on doing concreting and you keep on raising your tremie pipe. Once one segment is there, you remove that and again put the upper. So this is a continuous operation. You will keep on repeating it like this and till you reach here. You allow some overflow, as I told you, because this will be lattice. So even that's why you might have seen, you feel some concrete like thing is going waste. You allow some overflow, this lattice will go. And even after overflow also, as I told you, you cast pile more by some height than your design requirement, because that also we consider as a weak concrete, and then you chip it off. So this is how tremie concreting is done. Now the important thing is, number one, this, that you should not drop small concrete. Otherwise what will happen is that concrete will remain here or it will remain here and lattice will be in between. So initial pour should be of significant amount, so that when it falls here, it will, number one, bottom of tremie will be in this and it will replace this lattice, which is lighter in weight. And then once you start tremie concreting, you should not stop it till the end, because what will happen, यदि आपने बीच में बंद कर दिया, whatever is concrete in this, it will settle and your whole tremie pipe and everything you have to throw away. That is one thing. Second thing, when you withdraw, let us say you have done concreting up to here and then you have withdrawn the tremie, some lattice will remain here. Next time when you drop the concrete, there is a chance it may not get replaced. And number one, there will be a cold joint in the pipe, which is not advisable, and a weak layer which is of lattice, not of good concrete. So therefore, normally you always keep 100% redundancy. If you need one pump for tremie concreting, you keep two pumps. एक pump fail हो गया, दूसरे को immediately start करो, and if you stop in between, you are in for a big trouble. So then continuously you will keep on doing the concreting till you reach the end. So this is how tremie concreting is done. Clear?
Yes.
Any question about this?
Sir,
Yes.
सर ये ट्रीमी पाइप का एंड कैसे इंश्योर करते हैं कि ये कंक्रीट के अंदर ही रहे?
You know how much concreting is going on, how much volume is going on, and what is your bore dia. So the operator, he knows it, that how much with every pour, how much he has to lift. See, volume is, let us say concrete volume which you are putting inside is V, your pile dia is pi by 4 d square, then H will be this. H will be V by pi by 4 d square. So in one, this how much you are putting, that much only you will lift. So these operators, they know it, that at what speed. In fact, by experience, they know कि इस rate पे concrete flow आ रहा है, तो withdrawal has to be at this rate, every minute 1 centimeter or 2 centimeter. That they first calculate, and then by experience, it is continuously one side you are pouring concrete and other side you are lifting it up. Okay.
Okay, sir. Thank you.
Sir,
Yes.
in case of tremie concreting, the compaction is, sir, the compaction
No
is
compaction. No compaction.
compacting concrete, or there is
No. It's normal concrete. It's not self-compacting concrete, but it is not designed for any compaction. It is not designed for any. That's why I said it has got very high. We will see. It has got very high slump value, and its design is a bit different from others. There are some parameters are very different from others. High slump. And normally you have to, there another thing is its setting time is increased little bit, because everything it gets pumped comes here, thoda bahut bhi delay ho gaya to, so you add plasticizers, you add super plasticizers, those things are required to be added in this. No, what you call compaction is possible, and no compaction is done. No compaction, no curing. ठीक है?
Okay, sir. Yes, sir.
These things are reflected in its properties. These are the provisions of IES 2911 is in 3, 1, 2, 3, 4. I think 4 part. Then part 1 also has got section 1, 2, 3, 4 regarding board piles and their concrete and also IES 2911 part 1 section 2. It tells the what are the properties the concrete should have. It says concrete should be rich in cement, and cement content is more than 400 kg per cubic meter. You had quite high cement. Then high fluidity, that is the must. This requirement is must because it has to flow through trimmy. Then it must flow at the bottom. It must flow on its own. Should not create any blind spots and all. So slump value, as per IS code, it should be 150 to 180 mm. And as per IRC 78 is IRC code for bridges and foundations. It is 150 to 200 mm. And as I told you, sliding plug is pushed ahead of first charge to prevent mixing of water with concrete. That is also part of IS code. And trimmy to be watertight throughout the length. Otherwise, again, some water will enter and it will create problem. And attached to the hopper at the end with watertight connections. All connections, everything should be watertight. And diameter of trimmy pipe is, this is all IS code provision. Wherever IRC separate provision is there, I have indicated that diameter of trimmy pipe is 150 to 200 mm for the aggregates of size 20 to 25 mm. So here your porous aggregate also you use of smaller sizes. Normally you don't use fine aggregate and their size is less, 20 to 25 mm. And concreting should be uninterrupted, as I told you, and trimmy pipe bottom should always remain in concrete for 1 meter depth. 1 meter depth it must. So your first pour should be 1 meter plus something. Whatever was the gap between bottom of trimmy and all, you keep some gap, otherwise concrete will not flow. If this is your bore and you keep trimmy pipe here, how the concrete will flow? So you keep trimmy pipe here, some 3-4 inch above. So this plus 1 meter. So your first pour height should be this. That's how that your ball and those flap, they take care of this. Then concreting should be done above cutoff level. As I told you, whatever is your cutoff level, even though you allow some latents to flow even during concreting also, even after that also, whatever is your pile cutoff level, design level, minimum 600 above that you do concreting, because you still treat that in top. Some concreting will be mixed with the latents. And some length of concrete to be overflown towards the latents, as I told you. First you do overflow, then still you keep 600 mm minimum. Normally we used to keep, whatever sites I have worked, we used to follow a thumb rule of 1 meter. We used to do 1 meter extra, and then you chip it off. Okay, clear?
Yes, sir.
Yes, sir. Right. So this was about construction part of your piles, how you construct them and all various technologies and properties of concrete. Now something design. When you design the piles, what should be the reinforcement, what should be their spacing and all various provisions. So here, see provisions now, we have our own concrete bridge code where it says something about piles, does not say much about that many places. So then you have to depend on some other information. That information can be IRC code, it can be IS code as well, or maybe literature. So that's why I am trying to present what are various provisions. So for spacing of piles, for friction piles, generally not less than 3D. 3D is the diameter of pile if it is a circular pile, and if it is a square pile, which normally is not the case other than maybe a driven thing, then it is diameter of circumscribing circle for this is the diameter. This is taken as D. So for them, and friction pile, why we keep higher dia is because otherwise your friction will not mobilize. If your piles are too close to each other, their influence zone will start intersecting or disturbing each other. And for end bearing piles, it is not less than 2.5D. Friction piles not less than 3D, end bearing 2.5D, and maximum spacing 4D. Should not be too far apart also, otherwise the pile grouping action, what you call, may not mobilize. So normally 2.5 to 4 or 3 to 4 times D. That is what is the space. Pile bridge manual, if you read our Indian Railway bridge manual, it says normally we use 1 meter dia pile. That is what our bridge manual says. And IRC 78 for board piles, it says for river or marine bridges, where pile most of the time will be in river, it says it should be minimum 0.75 meter, and for bridges beyond water zone, minimum 1 meter. This is IRC provision. And IS code 2911 part 1 section 2, it of course says, but IS code, see, we must appreciate one thing, IS code is primarily from building point of view. So even though it is not stated anywhere, but it is mostly from building point of view. And that's why it says minimum 450 mm. In bridges, you will never see 450 mm anywhere. For railway bridges, as I told you, the most common dia is 1 to 1.5 meter, and there also 1.0 meter, 1.2 meter, and 1.5 meter. This is most common. Mostly you will find this. So this is the dia of the piles. Of course, there is a new technology, but it requires very sophisticated machinery. There are large dia piles. Sometimes people call them well piles also. Piles of 3 meter dia, piles of 4 meter dia. In fact, somewhere in metros also they are going for 2 meter dia piles. But then you need little bit different machinery. And large dia is entirely different. I think MES or BRO, I think the Metri bridge, which I went there once. I think BRO was doing that work, if I'm not wrong. Metri bridge, which is after Srinagar at the border of India and POK, or India and Pakistan, whatever you like to call it. There is a bridge there. They were there using 3 to 4 meter dia piles, but they are entirely different machinery and all, which comes from outside and all. Very high dia piles. Okay, now coming about concrete and steel in piles, RDSO manual. In fact, for well and pile, there is a RDSO manual which is only of 5 pages. I think it may be getting withdrawn anytime. They were telling they are working on that. It is very old, somewhere made in 70s, 80s. It hardly contains any information, very less information. So there are that manual. If you see, it does not give any specific provision about what sort of concrete. And this, as I told you, is a very brief 4 or 5 page document only. And concrete bridge code, that's why we follow based on environment condition. Your concrete bridge code must have been covered or will be getting covered. There they tell you from durability point of view, severe zone, which zone, minimum cement concrete, cement content, maximum cementitious content, and all those provisions, they will become applicable. And IS code says minimum M20 concrete, minimum cement 400 kg per meter cube, and when you are doing underwater, 10% extra. Some should be 100 to 80 mm, and if you are going to use TREMI, then 150 to 180 mm. Reinforcement, this IS code says minimum longitudinal reinforcement should be 0.4% of cross-sectional area, and you must use minimum 6 vertical bars. If you see the cross-section, normally your reinforcement will be like this. If you have seen the piles, mostly you put it on the surface and then ties or spirals, they are bound like this. And sometimes when you used to put heavy reinforcement, you put in bundles, 2 bars also. 2 bars here, 2 bars here, like this. Center, most of the time people put one, either you don't put much of reinforcement, you put on surface more. So it says there should be minimum 6 vertical bars, and the minimum spacing between these vertical bars should be 4 times maximum aggregate size, so that flow of concrete is not obstructed. Otherwise there will be hollow spots. And then links. Links means if you see this is the, so normally you provide ties or links like this. It can be a continuous spiral wire, or but normally you put these links or ties at different spacing. So there should be minimum 8 mm dia at 150 mm center to center, and then stiffer rings of 16 mm dia at every 1.5 meters. So 150, every 10th ring will be a ring of double the dia, stiffer rings. And minimum cover 50 mm. This is what IS code provision, and IRC provision is concrete should be M35, minimum cement content 400 kg per cubic meter, maximum water cement ratio 0.4, slump 50 mm minimum, and for trimming 150 to 200 mm. Reinforcement minimum 0.4%, maximum 2.5%. This is longitudinal reinforcement, vertical reinforcement, and vertical bar spacing or the splice or the link which you are putting, it should be 100 mm, and up to 2 bars can be bundled. Not splicing, sorry, this vertical bar spacing, this one. This is spacing, and as I told you, sometime bundling is done, so it permits bundling of 2 bar together, and this should be minimum 100 mm. This is assuming that your aggregate size is maximum 25 mm, basically 4 times. Links are minimum 8 mm at 150 mm center to center. Minimum cover here is 75 mm, whereas in IS code it was 50 mm. These are about cement and steel and their provisions when you design the pile. This is how it is proportioned. Okay, any question about this?
No, sir.
Next is load carrying capacity. How do you decide how much load pile will carry, or what you call the so-called design load for the pile? How will we arrive at? Now there are various approaches. All of them are approximate. Let me tell you one thing in the beginning itself. So the code says the ultimate load bearing capacity may be assessed by dynamic pile formula. There are many dynamic pile formula, and basically that uses the data. What you do is when you are driving the pile, or when you are driving the pile, especially for driven piles, when you are driving the pile, whatever resistance you are getting, it is measured by, there are several methods of measuring it. Using that resistance, you do the back calculation and you try to find out the pile capacity. That is one of the method. So which uses data obtained during driving the piles. Or you can use static pile formulas also. There are some static pile formulas you will see. There are many, not even one. Using those static pile formula also you can find out the load carrying capacity. Nowadays, of course, there are various finite element based software which give you the pile capacity. Very simple softwares are there. Even in Geo5 package which we have, there is a software for piles. So if you talk about static formula for non-cohesive soil, cohesionless soil, Healy's formula is more reliable. There is a formula called Healy's formula. There are many formulas, as I told you, and this formula and its details are given in Appendix B of IS 2911. But still it says in unknown areas load test is desirable. We will see load test also. As I told you, all these formula, all those things are based on some approximation, something. Even your geotechnical investigation you may be doing at one place, you don't do it every inch, but your soil data may be varying from place to place, even your depth. So many things. So the actual proof of pudding is in eating and not in preparing. So normally the most reliable estimation, you initially using whatever formula A, B, C, D, your software, static formula, dynamic formula, you do some analysis. Let us say your load is Q and your pile capacity is coming P. So then you will say, let us say Q by P will be number of piles and multiplied by something. Then this will be only initial estimation of the load. After that, what you will do is you will cast a pile at the site. Mostly initial pile load test you do on that. Mostly initial pile load test you don't do on a service pile. If you are very confident, you can do on a service pile also if you are sure it will not break. But when you are new, you can cast a pile outside and then you do pile load test on that, and that confirms that yes, whatever assumptions you have done, they are correct. That is one thing, initial load test. And then during work, again you do pile load test, routine pile load test, so that you keep on confirming that my pile is coming of the required capacity. So all these formulas are approximate thing to start with, or initial design. They are proven by using pile load test only, which we'll see shortly. So, and wherever scour is anticipated, skin friction must be taken into account only below the scour line. Naturally, I have told you that during scour, if this is your pile and you are expecting scour up to here, then you should not take friction account. Below this only you must take. Even there also in zone 4 and 5, in fact our code says, and most of the code says, you have to check it for liquefaction also, depending on type of soil. And if your soil is likely to get liquefied, then you don't even take this skin friction into account. So yeah, this is another important thing. Let us say this is your ground, and in between there is a layer of compressible fill, and your pile is passing through this layer. This is a compressible fill material. So when pile passes through compressible fill or sensitive clay, a drag down force is generated in this fill. This force, roughly estimated as cohesion of remolded clay multiplied by surface area of the pile shaft, must be added to the load. When you are driving your pile through this gets compresses because it is a compressible layer, and then it will give you drag down effect, and that force will work like this. That is basically frictional force around this. So that's why it says you take cohesion value C and area of shaft in this. That is acting in downward direction, sorry. Drag down force, it acts in downward direction. So it gets added with the load, or it is negative friction load. So whenever you are passing through a compressible area, please be aware of this. That value we must add to the pile load or deduct from the capacity, whatever you are getting. And then dynamic augment need not be considered on the pile. When you estimate the load on the pile, you will read this in bridge code. Live load is always live load plus its dynamic part. You multiply by CDA, coefficient of dynamic augment. So for pile load, dynamic part you don't consider, only static load you take. And settlement in pile you can calculate. There is a procedure given in clause 8 and 9 of IES-SIDHU. This is a very detailed procedure. Pile passing through cohesionless soil, pile passing through cohesive soils, then 2 layers, 3 layers, what is the properties of one layer with another, how draft is made, and very, very detailed procedure. I will not like to go into those details, that itself will take 1.5 hours. So that is a procedure given for calculating settlement of the piles. Because if you remember, we have said for any foundation, one is load carrying capacity, another is settlement should be within the limits. So we need to calculate the settlement. You can calculate that, and nowadays there are a lot of softwares available. By using that also you can calculate the settlement of the pile. So what is the static formula which we use for non-cohesive soil, or Hillis formula? It says QU, the capacity of pile, should be QP plus QS. And what are the various terms I will tell you. QP is your end bearing resistance. So QU is ultimate bearing capacity of the pile. QP is point or end bearing resistance, and QS is resistance due to skin friction. Very simple. Now, how do we calculate QP? QP will be equal to small qp multiplied by AP. AP is area of tip of the pile, this basically cross section. So QP is unit bearing capacity of pile for point area AP, and this is calculated like this: P0 into NQ, and it should not be more than QL. So now we will see what is P0, what is NQ. P0 is effective overburden pressure at pile tip. So if this is my pile tip, if this depth is whatever we said PF, then gamma times P. That is the overburden pressure at pile tip here. That is P0. NQ is your bearing capacity factor depending on phi value. We can take from IS code. So P0 multiplied by NQ will be QP, and it should not be more than QL. What is QL? QL is limiting value of unit point resistance. There are charts given in that appendix B of IS code. There are charts that what is the limiting value. So it should not be more than the limiting value. So now first part, simple equations of engineering mechanics. And skin friction, again very simple. Fs is average unit skin friction on pile shaft. What is the average value? And As is area of pile shaft. Pi by 4, not pi d, 2 pi r, whatever. So very simple engineering mechanics equation, static formula. Only thing, values of coefficients, how much we take, that's the thing. So with that, we can calculate what is the ultimate bearing capacity of the pile. And static formula for cohesive soil, that was for cohesionless soil. Now for cohesive soils, it says QU will be AP multiplied by NC into CP plus alpha times Ca. What they are? AP is cross-sectional area of pile, so pi by 4 d square. NC is bearing capacity. For given phi value, you calculate, or if phi is 0, this will be 5.14. And CP is average undrained cohesion as pile tip. Undrained cohesion value, you do undrained shear test and find out the C value from that at the pile tip soil, whatever the soil. So this is first part. And second part is plus alpha times Ca. Alpha is a reduction factor which is taken for board piles equal to 0.5 for stiff clays. And Ca is average undrained cohesion along length of pile. Now Cp is cohesion here, and Ca is this area, its average value or weighted average value you can take. And if same type of soil, then maybe Ca and Cp may be same also. So this is the formula, static formula for cohesive soil, which is given in IS code. So we have got formula for cohesionless soil, we have got formula for cohesive soil. In IS, another IS code, the methodology for settlement calculation of piles is given. This is static formula, simple formula. With this, prima facie or initial pile capacity can be determined. And this is Healy's formula. Again, that is normal static formula. This is Healy's formula, which is also given in Appendix B of IS 2911. This says QU is end bearing resistance plus skin friction resistance. End bearing resistance is given by this formula, and skin friction resistance is given by this formula. We will see one by one. Of course, very simple. AP is my cross-sectional area of pile at the tip. 0.5 D is diameter of pile shaft. Gamma is effective unit weight of soil at pile tip, because this is tip resistance. N gamma and NQ are bearing capacity factors depending on phi. And what is PD? PD is effective overburden pressure at pile tip. Same previous thing, only little bit more. The concept is same. So this is my end bearing resistance, and skin friction resistance is summation, because you may have 2-3 type of soil. So if there are 2-3 layer, every layer by layer we have to calculate. Ki is coefficient of earth pressure for I. We know how to calculate coefficient of earth pressure. PDI is effective overburden pressure for that layer. If we are calculating in second layer, let us say. So for this layer, what is K value? What is effective overburden? Equal to this 10 delta I. Delta is angle of friction between pile and soil layer in this, and ASI is surface area of pile in that layer. So like that, for every layer, you will calculate skin friction resistance, add it for all the layers. That is. So end bearing resistance and contribution from skin friction, both combined will give you QU. Clear? What are the formulas for pile capacity calculation?
Yes, sir.
Yes, sir.
Yes, sir. Yes, sir.
Now, you sometimes permit some overloading of piles also. Now, when do we permit and how much is permitted? Let us see. Now, you design a pile for a standard allowable load, as I told you. And later on, when you check it by pile load test or something, in design time, you don't take any allowance, whatever factor of safety, everything you do and find out. But it is, this pile is found to be short of that load when you do pile load test, and it can be due to many reasons. Change in design during construction, maybe some change was there in design of pile, some reinforcement changed or something happened. or construction inaccuracies. During construction, what you designed and construction, something wrong has happened, or as a outcome of pile load test. Normally this happens, both of them they will get reflected here. So if your pile capacity is reduced due to some reason, actual pile capacity, then what you have initially thought of, then it says to be overloaded as under what 10% of pile capacity on each pile. So each pile, if its capacity we have taken 1 P, then we can take 1.1 P individual pile, and maximum overloading on a group of pile is restricted to 40% of allowable load on a single pile. So if there are 4 piles, maximum overload in this group will be 40% of allowable load on a single pile. Means if this was P, then on a group maximum you will allow 0.45 P. Maximum, whatever group capacity, let us say PG was group capacity, then PG you can allow 0.4 times P, that much overloading. But as I told you, it is never done at the end. It does not happen that my pile is P, so I design for 0.9 P. No, this is to take into account anything unforeseen which has happened during construction. For that, you can allow some overloading on the pile from its initially designed capacity. So that is what is the provision regarding overloading of piles. Another important issue in piles, especially for end bearing pile. Now we have said this is rock, and end bearing pile transfers the load by end bearing resistance. But it does not stop at the rock itself. For this action to mobilize, you take pile little bit down in the rock and start from here. This is known as socketing. This is known as socketing. Now this is a big debate. Really speaking, it is not given anywhere. People, we also when we worked in the field, this used to be a big question. Is ab socketing kitna dena hai? Rock mein kitna socketing dena hai? And if you are 10 people, they will probably give you 20 answer, if not 10. But that's why I have tried to put all the facts in front of you. What are various provisions? RDSO manual, it does not say anything about socketing. IRC 78, it says for hinged piles resting in rock. If you have designed pile at the end as a hinge, you are not taken as a fixed support. That is what we normally do in modeling. In that case, it says if unconfined compressive strength of rock, as I told you yesterday also for rocks, you take a cylinder of dia 5 centimeter and height 10 centimeter and do unconfined compression test. This QU is unconfined compressive strength. So if unconfined compressive strength is more than 12.5 megapascal, then it says 0.6 meter. Take the socketing. And if rock more than 12.5, rock is very good. And if unconfined compressive strength is between 2.5 to 12.5 megapascal, then give more. Weaker is the rock, more socketing you need, so that it develops that end bearing action there. This is what is given in IRC 78. If you read literature, many of the books like Tomlinson and or these major books on piles, it says for basalt, basalt means very, very strong rock, basalts, granite and this sort of rocks, 0.5 times the pile dia. So if you take pile dia 1 to 1.5 meter, it almost comes 0.6 meter. It comes close to that. And high to moderately weathered rocks like trachyte, rocks which are not very strong but highly in between, D. So how much? 1 to 1.5 meter, coming close to this. And volcanic breccia, I don't know whether you've seen breccia. Breccia is type of rock which comes in flakes and flakes and flakes. When it is under compression, it is okay. If you expose it to sun and all, you can break it with hands also. So it's highly weathered, highly disintegrated rock. For that, it says 3D. You may have to go up to 3 times D, maybe 3 to 4 meter. This is what literature says. Okay, so we are getting value of 0.6 meter, 1.5 meter, around 0.6, around 1.5, and highly weathered rock, maybe 3D. And then there is IS 14953/1998. It says for sound, relatively homogeneous rocks like granite, gneiss, basalt and all, 1D to 2D. And moderately weathered, closely jointed rock, including schist or like slate, 2D to 3D. These values are on high side, but there is a catch. soft rock or sedimentary rock, which includes hard shale, sandstone, siltstone, 3D to 4D. These values are very high, but then it says these values are for preliminary design of pile only. He says you design a pile, do the initial load test, and then refine these values. So these values are actually on high side. Now what else is given? It says actual requirement to be estimated from static computation given in the code and verified in load test. It has given a computational method also. It says you try to do that and then refine it and finally verify in the pile load test. If your capacity is coming very high than the design, reduce the socket. So they are on higher side. The code also says it. And internationally, if you try to see what is the practice, Germany, end anchored piles, they call it end bearing or end anchored piles. If your ultimate strength is more than 5 kilopascal, meganewton per is megapascal, then 0.5 meter socketing, and if it is less than 0.5 megapascal, then 2.5 meter. In Hong Kong, these are two documents, BD 2004 close 2.2, and there is an ADS, this document. They call it for grade 1 rock. Grade 1 rock, UCS more than 75 megapascal, and UCS more than 50, grade 2, UCS more than 25, grade 3, 0.5 meter, 0.5 meter, 0.3 meter, and ADS, this code says 0.6 meter. So here also you are getting value of around 0.5, 0.6. In USA, there is code IBC 2009, it says minimum 1D. UK, Australia code, at least we could not find what is the value. And in India, IRC 78, we have already seen that when unconfined compressive strength is more than 12.5, it is 0.6 meter. And when unconfined compressive strength is between 2.5 to 12.5, it is 1.5 meter. So these are various values, and in field I will tell you what people generally follow in railways. If your rock is very hard, this is granite and basalt, this type of rocks, you give 0.5, 0.6, 0.7, that much. And in any case, of course, you are doing pile load test. And if your rock is weak, sandstone or this sort of rocks, then you give 1 meter or 1.1, 1.2 like that. This is the normally followed procedure regarding socketing. Then another issue in pile is permissible tolerances for piles, means locational tolerances. There can be two things in pile and well which happen. This is, let us say, pile. One is called shift. Your pile vertically remains same, but it shifts. And another is called tilt. It tilted like this. Angle has changed. Tilt. You can measure tilt in degrees or 1 in whatever. So how much locational inaccuracy is permitted? So for RDSO manual, it does not give any clear guideline. If you see IS 2911 part 1 section 2, then it says angular deviation. Angular deviation means tilt. Vertical piles, it should not be more than 1.5%. And shift, that is vertically remain same, shift. So piles less than 600 mm dia, 75 mm or D by 6 is the shift permitted, and for piles more than 600 mm dia, 75 mm or D by 10, whichever is less. So these are the shift and tilt permitted as per IS code. And then what it says, if there is an excess deviation, let us say your pile has shifted more than shift, or maybe it has tilted more than this, then it says you number one, your location will shift to you. So redesign the pile cap, and if it is not possible to do so, then pile should be replaced or supplemented by additional pile. Let's say put another pile or replace this. Don't take that pile into account. So this is IS code provision. And what IRC 78? Angular deviation tilt 1 in 150 and shift 75 mm. So 1.5%, 1 in 150, 1.5%, and 75, almost same as IS 2911. These are the permissible tolerances. Another issue is single pile and pile group. No pile you put as a single pipe. Normally you will see there will be 4 piles or 6 piles and there will be a pile cap. So it is not that its group capacity will be 4 times P. That is, it does not happen. So your capacity which you will get in load test will be individual piles, but actually finally piles will be in the group. So for pile group, the bearing capacity of pile group is evaluated by multiplying with what is known as efficiency factor. Now this efficiency factor, getting efficiency factor is a difficult job. There are many equations for efficiency factor, but it is difficult to establish their accuracy as it depends on many complex factors: the spacing, the diameter, the type of soil, the driving method, the casting method. So many things depend. So therefore, it is desirable to consider each case on its own merit. However, full-scale trials have shown that piles driven into soft to medium clay with 3D to 4D spacing, as we have said, 3D to 4D or 2.5 to 4D, the ultimate group capacity is only 2/3 of sum of single pile capacity. So if you have got each pile capacity P and you have got 4 pile, then total capacity will be 2/3 roughly. And nowadays, of course, for very important structures, people do numerical modeling. Even pile group load test is done sometime to check what is the efficiency factor or what is the capacity of pile group. And these are again some guidelines given in literature and all. The dense sand not underlain by weak deposits, means it is not that on top those dense sand and below that weak layers are there. And if a type of pile is driven, then your bearing capacity is number of piles into SPC, means you are single pile capacity, no reduction. If it is loose sandy soil and it is a driven pile, then it is half. Efficiency factor is 0.5, number of piles and bearing capacity of the capacity of individual pile. And again, sand not underlain by weak deposits, and if it is bored pile, then this factor is 2/3. So 2/3 to half people take the efficiency factor, or maybe 100%. 100% rarely it is taken. So capacity of individual pile vis-a-vis capacity of group pile. Again, as I told you, when important jobs are there and all, nowadays what people do is they do modeling, numerical modeling, and then you do its verification, its validation at the site by pile load test. Okay, clear up to here?
Yes, sir.
Yes, sir.
Last part is pile load test. Since we have said that pile load test is a final proof of the pudding, so how do we do pile load test? This is given in IES 2911 part 4, and there are 2 types of tests, as I told you, initial test and routine test. So initial test is conducted at initial stage, where you load the pile up to ultimate load or 2.5 times the safe load, whichever occurs earlier. And why the initial test is required? Number 1, you determine the ultimate load carrying capacity and arrival of safe load by application of a factor of safety. You determine what is the ultimate load carrying capacity of this pile, and divided by suitable factor of safety, you will get the safe load. That's the purpose of initial pile load test, one purpose. Second thing is to provide guidelines for setting up the limits for acceptance for routine test. From this, you will get a benchmark value from pile load test, initial pile load test, and that values with whatever multiplication, division and all required, we'll see, you have to get in routine test, further test during. This is before starting mass work. And then to get an idea of suitability of piling system. Yes, maybe you might have designed pile on paper and all, but see whether what pile you are casting at that site, you are getting that much of load carrying capacity or not. If you are not getting, then maybe you have to think of piling system or some changes in your system. And to have a check on calculated load by dynamic or static approach. So this we have seen. You calculate load by whatever dynamic formula, static formula, IES formula and all. But how close or how far those test loads are from your actual load, that idea you will get from this load. And the number of piles for initial load test are given in IS code. It says in your project, if total number of piles are less than 1000, then you must do on 2 piles. 2 numbers minimum pile, you must do pile load test, each pile individually. And if your number of piles in project are more than 1000, then 2 numbers of course, plus additional 1 number for every extra 1000 or part thereof. So first 1002, then for every next 1000, 1 test for your pile. That is the number of piles on which you have to do initial pile load test. And routine test you do on working piles, whatever you are at site actual pile. Even initial test also, if you are confident, you can do on working pile, but then if you put good on working pile and if it fails, it can cause hell of a problem. So if you are not confident, do it, cast it on the site, that much of pile very near to site, and test them. And why they are required? Number 1, check the safe load from static analysis. That was for ultimate load initial file. Here the safe load, what factor of safety you applied and other things, or whether it is coming closer to that. Another thing is detection of any unusual performance contrary to the finding of initial test. Let us say initial test, you have found out some capacity of pile. And during routine test, if you suddenly find that there is a lot of change in that capacity, it tells you something different has happened. Either bore has collapsed, or some there is your mix is not proper, or reinforcement has not gone properly. Something has changed from your initially designed and tested in the initial test pile. So you have to relook on your process. Workmanship check also, that workmanship is correct. Concrete pouring, concrete everything is as per initially thought program. And the number of piles required for routine test is 0.5% of total number of piles subjected to minimum 1. 0.5% or whatever number of piles in your project, that is your initial test. And this can be increased up to 2% depending upon the nature, type of structure and substrate. If your structure is very important, maybe you may like to do 1%, you may like to do 2% also. If your substrata is changing very, very fast, there are a lot of variations, then you will like to do little bit more tests so that you are confident that nothing wrong has happened. So these were the type of test, and the test procedure is like this. So this is your ground level, this is your pile. Here you will have some reinforcement also portraying. So chip of the pile head to horizontal plane till sound concrete is met. Chip it off, take some mechanical, cut this reinforcement chip concrete also and make it a level good surface. Cut off the projecting reinforcement and finish the top smoothly with cement plaster. Here apply a thin layer of cement plaster so that a very smooth surface is there, because you will put jack on this and other equipment. So for their seating, prepare the pile. Then place a bearing plate with mark at the center. This is like normal plate load test. So this is your pile. So you will put a bearing plate here. In this center there is a mark on head of pile where your jacks will rest. Then apply the test load in series of, now you know what is your pile capacity, you calculated, ultimate capacity you calculated. So you apply this load in a series of downward incremental load. It is applied in stages like any pile load test, and each increment being about 20% of safe load on the pile. So whatever load for which you are going to test the pile, divide into 5 increments, 20, 40, 60, 80, 100. And then you use load cells for measuring the load. And the reaction for 25% more than the final load on the test pile, you apply more 25% more than your whatever you have. So you go to 1.25 times the capacity, can be obtained from following methods. So not apply, actually you must have that much of reaction. Now for applying, let us say this is your pile and you are applying some load. So how do you apply? You have to take some reaction. So capacity of this reaction system should be 25% more than the maximum load which you are likely to apply. Otherwise it will get uprooted. And there are various methods of applying them. Most common is cantilage for reaction. Here, this is your pile, this is your jack and load cell and all. So here you will put some stone blocks or cribs or something. Over that you will put a beam and you will make a platform like that. And over platform you will put lot of weight. It can be concrete blocks, it can be sand bags or whatever. A physical load over that. over the cantilage like this. Here you can see this is the platform, and over that you put all this large number of blocks. You can put cement bags, whatever you want to put. That is cantilage system for reaction. Another system you use anchor piles for reaction. So here this is your main pile, test pile. Here you are applying the load. You put two anchor piles of adequate capacity, and through that you take two HTS wires. They go through a beam, and here you anchor them. So now these piles, they take the reaction. Here you can see there are two anchor piles, and this is your main pile. So here you to cast two anchor piles or construct two anchor piles also. And in this case, the center to center distance from test pile, this distance, it should not be less than 3D or minimum 2 meter. It should be more than 2 meter or more than 3D times. Otherwise, capacity of this pile will start interfering with capacity of this pile. So you can put anchor piles. Another system which is used is rock anchors for reaction. In this, what you do is either there is a sound rock, or what you do is you first put anchor rods by drilling small dia pipes and then do grouting here through these anchor rods. So it develops some anchorage, and then that is taken through this reaction beam. You tighten it here, and this takes the reaction. So rather than anchor piles, you put rock anchors. And the distance from edge of pile being 2D or 1.5 meter, like previous 3D or 2 meter. In this case, from here to here, this distance, there should be sufficient distance so that this is not interfering with working of this piles. That is rock anchors for reaction. Then you record the settlement, and minimum 4 dial gauges are used so that any twist effect or something, it gets averaged out, and their sensitivity or least count is 0.01 mm like any other plate load test. And dial gates should be placed symmetrically and at equal distance from test pile. If you see plan, if this was your test pile, normally you put two, this balancing sort of thing, and you put 4 dial gauges here. So you measure the settlement. And they are held by datum bars, as I told you, resting on immovable support at a distance of 3D from edge of pile. This datum bar also, their support should be at least 3D away from the edge of the pile. Again, idea is external thing, that disturbance should not come into the behavior of the pile. And preferably to use remotely controlled LVDTs with digital. Nowadays, you might have seen in the lab also, rather than using dial gauges, people use LVDT, linear variable differential transducers. They are their electronic equipment, they are connected to some other. You can see that displacement rather than going अपना, वरना सिर घुसाना पड़ेगा फाइल के नीचे, फिर उसका डायल गेज का रीडिंग लेना पड़ेगा. Here you sit on your chair with a cup of tea or coffee, and in front of you there is a screen. LVDT का रीडिंग उस स्क्रीन पे सीधा आता रहता है. यहाँ आपने लैब में भी देखा होगा, for many tests now most of the tests there are LVDTs, and there you don't keep on seeing those readings. Those readings are captured and they are displayed on a processor and on a computer in front of you. This is what. तो आपने load हो गया, settlement हो गया. Then safe vertical load from initial test. What will be the safe vertical load? So for piles less than 600 mm dia, as per IES code, it will be least of the following. Number 1. So now then you will plot load settlement curve of the pile. So for piles less than 600 mm dia, first is 2/3 of the load for total displacement of 12 mm. 12 mm vertical displacement के लिए जितना load है उसकी 2/3 value, और 50% of the final load at which total displacement is 0.1 times diameter of the your pile. This is for piles of dia less than 600 mm, lesser of the two values, and for piles of dia more than 600 mm dia, 2/3 of the load for total displacement of 18 mm or 0.02 d, whichever is less, first, and 50% of final load at which total displacement is 0.1 d. So this is second. It's only addition here is 12 mm की जगह 18 mm है plus 0.02 d भी है. So based on, normally as I told you, our piles are in this category. So this will be the applicable provision for us. And safe vertical load from routine test, it will be 1.5 times the working load, with settlement at test load being not greater than 12 mm for piles less than 600 mm dia, and 18 mm or 0.02, whichever is less for pile. So for this 18 mm or 0.02D, basically this only. For this 1.5 times of this will be the safe vertical load for these piles. So this is how you do pile load test. Okay, pile load test, any doubt?
No, sir.
No, sir.
No, sir.
Now coming to factor of safety, you ultimate load and working load or safe load. What should be the factor of safety? RDSO manual says use factor of safety of 2.5 if you derived the capacity from static formula. IRC 78 says take value of 2.5 for piles in soil if you have derived from static formula, and 3 for piles in rock if you have derived the capacity from static formula. So 2.5 and 3 for soil and rock. In rock, you always take factor of safety more, and IES code says 2.5. So 2.5 or 3, whatever you want to take, you can take that as factor of safety. So whatever is your ultimate load carrying capacity from your static formula, divide by this, that will be your safe load carrying capacity of your pipe. Okay, this is also okay.
Sir.
Right, now last thing probably is integrity testing. Now, as we were discussing other day also, see, we have taken all the precautions, everything, but still when I have put my concrete here, whether some necking was there, whether some bulging was there, whether some cold seam has developed, whether some latence has remained here, it's very difficult to find out in these piles. So for that purpose, various methods have been developed. One is, it is not testing, I have not written here, but which is used very commonly now, is what is known as CHUM test. CHUM, cross hole ultrasonic monitoring. CHUM. This is what is called as cross hole ultrasonic monitoring. What is done in this? Let me see. Here. No. Just 1 minute में देखता हूँ मेरे पास वीडियो हुआ तो मैं आपको दिखा देता हूँ. Okay, I will tell you otherwise here how what is done in cross hole ultrasonic monitoring. If you see the cross section of your pile, let us say this is your ring, these are the reinforcement bars. What you do is you provide normally 4 25 to 50 mm, 50 mm is very common, tubes here in this and tie them properly. And if you see inside, this is your pile, these tubes also will get lowered with this your reinforcement and they will remain hollow. इसमें concreting नहीं होगी, बाकी सब में concreting हो जाएगी. Now there are ultrasonic sensors which you lower in these tubes. Normally you use 2 tubes at a time, this and this, and then you do in this and this. So this ultrasonic sensors are lowered in this, and this one is receiver, another is transmitter. So this transmits ultrasonic signal which this will receive and something will reflect back and come, and then you pull them out at the constant velocity. So both of them are here next time, then they are here, then they are here, and these signals are recorded in a processor, in a equipment, and then it is processed. So these signals, see, if there is no discontinuity, then time this takes to go there, this receives, that is constant. Then from this it comes back and again goes there, then second receive, that is constant, that is recorded, and based on that some charts are plotted like this. So if your chart is coming like this, means uniform. Suddenly if there is something wrong, if this time is increasing somewhere, it means there is some discontinuity here. Then you put it in another 2 holes and pull it out. This is a very common test nowadays, chum test people call it, cross hole ultrasonic monitoring, and that is one way of checking the integrity. After checking integrity and all, sometimes people leave it as it is. In future also you can check it, or otherwise if you don't want, you can put a cement grout here and close it. But normally people keep it because your loss in area is very less, that you can take into account. Keep them so that in future also if you want to check the integrity, you can check it. That is one. There are another method which are known as low strain integrity test. So first of all, why integrity test is required? In majority of the cases, the cast in situ piles fail because of pile shaft necking, discontinuity of concrete, intrusion of foreign matter, and improper toe formation due to contamination of concrete at the base. आपने एक साथ significant concrete का mass नीचे नहीं गिराया ट्रेमी वगैरह में, then some latents may get trapped at the toe of the pile and your full end bearing action may not mobilize. Cracks develop while handling precast pile can also be a cause of failure. Precast में यदि crack develop हो गया handling में या driving में, hence pile integrity assessment before completion of pile caps is very important. Nowadays, in fact, railway में भी आप देखेंगे, wherever you have significant में भी 10-20 pile भी हैं, CRS insist करता है कि या तो आप क्रॉस और अल्ट्रासोनिक मॉनिटरिंग के रिजल्ट मुझे लाके दो, otherwise at least pile integrity test आप लाके दीजिए. You please get it done. Normally, it is insisted upon. So the low strain integrity test, there are 2 type of pile load test. One is high strain integrity test, जिसमें बहुत बड़ा सा लोड आप उस पे गिराते हैं. That was done in old time. वहाँ पाइल के ऊपर एक पाइल हेड बनाना पड़ता था and all. Like this is your pile, यहाँ एक हेड बना के टोपी सी उस पे. High strain integrity tests, they are not anymore used. Low strain integrity tests are used. Out of the one which is very common is known as sonic echo testing. There is a IES code for that also, IES-14893. This has been used successfully for checking the integrity of piles after installation. This is a quick and simple method. Of course, it needs a very experienced person to interpret. It is like ECG. ECG तो कोई भी मेरे जैसा आदमी बटन दबा के कर ले, लेकिन उसको समझने वाला चाहना must be rare कि उस ECG से मतलब क्या निकल रहा है. That is more important. So it does not identify all imperfections in a pile. Please understand, but it provides you information about continuity. यदि continuity कहीं break हो रही है, this test will tell you either due to latents coming in between or cold joint or defects such as cracks, necking में उसका cross sectional area change हो जाएगा, soil intrusion आ गया, continuity disturb होगी, changes in cross section, it will tell you, and it will also tell you the approximate pile length. Unless pile is very long or the skin friction is too high, then there may be error. Otherwise tells you pile length also, कि pile कितनी length तक गया है. ऐसा तो नहीं है आपने कॉन्ट्रैक्टर को कहा 25 मीटर करना है and he did 20 मीटर and he says हो गया 25 मीटर. How will you measure? Of course, normally during piling you are supposed to be at the site. First you have to give him permission कि हाँ अब concrete pour करो, pouring permit we used to call it, and then you be available all the time at. Otherwise pile होने के बाद में कुछ नहीं पता चलना. So this sonic echo testing is a low strain integrity testing as per this IS code. Here I will show you a small metal or hard rubber hammer is used to produce a light tap on the top of pile. एक छोटा सा हैमर होता है, अभी मैं दिखाऊं, उसको आप पाइल के टॉप पे टैप करते हैं with some effort. Then it creates a sonic wave. This wave traveling down the length of pile is reflected back from toe of the pile. ये यहाँ से ऐसे जाके रिफ्लेक्ट होके ऐसे आती है, फिर आप इसकी लोकेशन चेंज करते रहते हैं. And it is recorded through a suitable transducer or accelerometer which is held here on the top of pile. And travel time उसका जो है वो login हो जाता है. So this is how it looks like. This is your hammer. छोटा सा हैमर है, ये रिसीवर है, तो आपने यहाँ ये दिया, यदि ऐसे, यदि बीच में डिसकंटिन्यूटी हुई तो यहीं से लौट जाएगा. you will know. और नेकिंग हुई, आप जब इसको थोड़ा इधर करके देखेंगे तो ये कहीं इसमें फंस जाएगा. That will give you an idea. So similarly जहाँ बल्ब लेंथ होता है यहाँ डेंसिटी कम हो जाएगी, so its travel time will change like that. This is the principle of this test, and this is, ये इसको experienced आदमी पढ़ सके. This is the sonic echo data. Now seeing the sonic echo data, the person will tell you this is how ये hammer है, ये accelerometer है, ये उसकी केबल वगैरह है. And analyzing this data, it tells you कि सब ठीक है कि नहीं है. This is this console looks like. So if the pile has any imperfections or discontinuities, these will set up secondary reflections which will be added to the return signal. एक तो आपका reflection का time change होगा, दूसरा secondary reflection आएगा, second reflection आएगा, and that will tell you probably the location of the defect also. And by analysis of captured signal and a knowledge of the condition of the ground, age of concrete sets, depending on signal कितने time में आएगा, that will depend on how is the soil, what is the concrete density and all. So this is how they do the calibration. A picture of location of such problem can be built. That's why I said requires an हमारे से आपसे नहीं होगा. It requires an experienced person. And normally you do more than one recording until repeatability of signal. Same pile पे आप 2-3 बार record करते हैं. And if you get the same signal at the same location, it means ठीक आ रहे हैं result. There is no other problem. And this test should be, as I told you, performed and interpreted by a trained and experienced person. We should not try to do it ourselves. It is done by an experienced person. Okay, clear? What are the integrity? That day I think Pramit was asking this question that why don't we lower a camera and all. So in that same chum recess, people keep it during service life. You can put a camera also, and from other end you can see, or otherwise some sort of ultrasonic receiver and transmitter we can do during testing. ठीक है? Okay. These are further references or readings if any one of you wants to go into further detail, because in 2 hours more than this is not possible. I think, and this should be sufficient for you till you go to J grade, I think. How they are constructed, what are various design parameters, how their capacity checked, what are other tests. Further, if you want, then as I told you, this is that RDSO manual on design and construction of pile foundation. In 1985 it was made. It is about to be withdrawn. It is this 4-5 page document, hardly says anything. It is available on RDSO website also. And then IES 2911 part 1 2010. Part 1 is about design and construction of pile foundation, concrete pile. Something is for timber pile and something for other. Section 1 is driven cast in situ concrete pile. Section 2 is board cast in situ concrete pile, and section 3 is driven precast concrete pile. All 3 type of pile. One section is there. Then IES 2911 part 3 is for under rimmed piles. If you are